Oh, I also graded your projects, finally, and those are in the grade book. So I will put your quizzes in the grade book hopefully after this class. No, I wrote them down. So, okay, so we are going to talk about Taylor polynomials, and this is going to lead us into some discussions about power series, about Taylor series, all sorts of cool things. So we will need our converging and diverging knowledge with our series, so that when we get into 9.8, 9.9, and 9.10, we can do some other things. So right now you're not going to see a big connection, but next week we'll start to see some pieces come together. Okay, so the first thing we need to talk about in terms of moving forward in chapter 9 are Taylor polynomials. Okay, this is Brooke Taylor. He was the one who published the idea of Taylor polynomials. Okay, now I'm going to go ahead and let you just like put your pencils down. You're not going to have to write this right now. Okay, so suppose we wanted to find a 4th degree polynomial that approximates the behavior of this natural log graph at 0. Okay, why would we want to do this? What is nice about polynomials? Okay, what else? The derivatives are very nice and they give us a lot of information. Okay, we know how to graph them without a calculator pretty easily. Okay, so polynomials are by far the easiest type of equation to work with, especially when we're talking about graphing and taking derivatives and using them to interpret. Okay, so what we're going to do is we're going to take this natural log graph and we're going to look at the place where x is 0, and we're going to try to build a polynomial that does the same thing there. Okay, so what we're going to do is we want p of 0 polynomial and f of 0 to be the same thing. We want the first derivative to be the same thing. We want the second derivative to be the same thing. We want the third derivative, the fourth derivative to be the same. That way, our curve looks like our natural log curve, at least right by 0. Okay, so here is our polynomial and our function. Gosh, I hate the lag on this thing. Okay, so I just made a 0, a 1, a 2, a 3, a 4. Those are our coefficients for the respective terms, x to the 0, x to the first. Okay, so let's think about this. When we plug in 0 to f of x, we get 0. When we plug in 0 for our polynomial, these all go away and we get a sub 0. So what needs to be true? Okay, now we want our first derivatives to be the same. So I'm going to take the derivative of the natural log of x plus 1 to get 1 over, I don't know why I wrote it 1 plus x, but potato, potato, right? Commutative property. Okay, when we plug in 0, we get 1. Are we okay with that? When we take the derivative of p, the derivative of a constant is 0, and then we do the power rule to get a sub 1, power rule to get 2, a sub 2x, etc., etc. Are you okay with our power rule? Okay, well, when we plug 0 into this derivative, all of these are going to go away, and we're left with a sub 1. So what do we know about a sub 1? Okay, let's go to the next one. 1 plus x to the negative first power has this derivative. Do you agree? And when you plug in 0, we get -1. If we take P prime and we do the power rule, a sub 1 goes away because that's a constant. Power rule, power rule, power rule. Are you okay with that derivative? Okay, well, if we plug in 0 for x, those terms go to 0 and we're left with 2a sub 2. Well, if I want our second derivatives to be the same, then I want 2a sub 2 to equal -1. So what's a sub 2? Oh, good. Interesting. All right. Now, -1 plus x to the -2nd power as this derivative. When we plug in 0 for x, we would get 2. Okay. When we take the derivative of p double prime, what's wrong? Yeah. The clock.
No, it's like something out there. It's like back, yeah.
I don't know. I'm sorry. So when we do the power rule here, 2a sub 2 is a constant, so that derivative is 0. Power rule, power rule. If we plug in 0, the 24a sub 4x goes away. Okay. So what needs to be true? We want 6a sub 3 to equal 2. I hear the clock ticking. Yeah, I hear it.
Yeah. We're not crazy.
I don't know what it is. Okay, last one, fourth derivative. If we have 1 plus x to the -3, then here's our derivative, -6, 1 plus x to the -4. We plug in 0 and we get -6. Okay. If we do the derivative of p triple prime, the derivative of a constant is 0, and this is just 24a sub 4. So we know that -6 needs to equal 24a sub 4, aka a sub 4 is, and I know that we could reduce this, but to see the pattern, I'm gonna keep it like this. Okay, so here's our polynomial. Ready? Yeah. I want to show you something. There we go. All right, so here's our graph. So here's y equals 0. Plus 1x. Ooh, that got closer. Minus 1/2 x squared. Plus 2/6 x cubed. Are you seeing this? How cool is this? Okay. Plus, nope, minus 6/24 x to the 4th. If I zoom in, you can't even tell which one is which. But close as what do you think is going to make this even a better approximation? more terms. That's where we're eventually going to be going. Okay. Okay, so I want you to look at this right here. Does anybody you want to participate in a positive way or negative way? Because right now I'm about to just send you out in the hallway and you can watch this video later. You're riling up everybody else. Imagine these denominators are 1. 1, 1, 2, 6, 24. Yes, those are factorials. Where are they coming from? Every time we took the power rule, the power kept getting multiplied down. Okay, so this particular polynomial has the form f of 0 over 0 factorial plus f of 1 over 1 factorial plus f prime of 0 over 1 factorial x. Second derivative of 0 over 2 factorial x squared, etc., etc., etc. And we could keep going if we wanted a better approximation. Okay, so here we go. Specifically, when we're centered at 0, this is the pattern of a Maclaurin polynomial. Yes. Nice catch. Okay. This is a Taylor polynomial centered anywhere. Specifically, a Maclaurin polynomial is going to be centered at 0. So you're going to write both of these down. Go ahead.
that the first time that you heard those?
No. I was hearing it last night, but then I was just like. Okay, do you remember? Well, back when you were learning your shapes, you have a rectangle and a square. Is a square a rectangle? Yes, it's just special. A Maclaurin, is it not? It's special, right? It's a special rectangle. Okay. A Maclaurin polynomial. A Maclaurin polynomial is like a square. Okay. It's a Taylor polynomial. It's just has one extra specification. It needs to be generated at 0. Okay. Here is a Taylor polynomial. Generated at A. Okay. So notice how in all of these, okay, the second derivative is over 2 factorial is with x squared. The third derivative is over 3 factorial is connected to x cubed. If you can remember that pattern, you're going to be fine. is this. It's this.
You have to go stand on it.
Well, I was trying to figure out where my ear was taking me. I think it's a thermostat.
You stop it by hitting it.
Yep. Just for you. Well, what's 0 factorial? And what's 1 factorial? So yes, but we're just not gonna write them because it's not necessary. Okay, did you hear Grace's question? This one technically is over 0 factorial, and this one technically over 1 factorial, but both 0 factorial and 1 factorial are 1. So you don't necessarily have to evaluate them. Okay. So we're gonna go back to the example that I went through. Yep. Rachel went to La La Land for a minute. All right, so we're gonna go back to the example that I started the class with, but we're actually going to find it like you will moving forward in your homework, okay? So what do we need for each term? We need function value. We need first derivative, second derivative, third derivative, etc. What? Yep. So, but this is, I want to go through it now that we know what we're doing. Okay. So our function is the natural log of x plus 1. What is f of 0? Thank you. Our first derivative is x plus, well, 1 over x plus 1. What do we get when we plug in 0? Our second derivative, negative 1, x plus 1 to the negative 2. What do we get when we plug in 0? Why is it what? You told me 1/2. It's all Grace's fault. Okay, third derivative would be positive 2 x plus 1 to the negative third. What do we get when we plug in 0? No, she's 2.
Yes.
Our fourth derivative, negative 6 x plus 1 to the negative fourth. When we evaluate it at 0, we get what is the problem? What's the issue? Okay. So maybe like the constant conversation and laughter can dial it down a little bit. Okay. So when we actually write our polynomial, P for polynomial, we have f of 0 plus f of 1 times x to the first plus second derivative over 2 factorial x squared plus 2 over 3 factorial x cubed plus negative 6 over 4 factorial x to the fourth. I'm pretty flexible in terms of you leaving it like this, you simplifying. I'm not really worried about it as long as you get me the polynomial that I want. No, it just is the derivative. In this case, we are going to get that to happen because of this, and we're plugging in 0, but that's not going to happen. Okay. So let's maybe look at a different one. So here, write a, what is happening? And let's replace series with polynomial. Excited about this one. Right? Okay, our function is cosine of x. What's f of 0? Okay. Our derivative, negative sine x. Plug in 0. Second derivative would be negative cosine of x. Evaluated at 0. You're getting excited, right? Third derivative is sine of x, evaluated at 0, is 1. Now, what's going to continue to happen? Oh, you're paying attention. That's good. Thanks, guys. We're going to go through this same cycle again, aren't we? We're going to go 1, 0, negative 1, 0, 1, 0, negative 1, 0, right? So our polynomial, our polynomial is going to be 1 plus 0x plus negative 1 over 2 factorial x squared plus 0x cubed plus 1 over 4 factorial x to the fourth. And because we know what's happening, what's going to be the next term? Okay, 0x to the, yep, then plus 1 over 8 x to the 8th, 8 factorial, right? And then we can keep going on and on and on if we want to. And that is where this is going, is eventually we're going to write this as a series, but that's going to be here in about a week and a half. Okay. Now let's go back to Desmos. What's wrong? Okay, so the cosine of x. So we have y equals 1. And then did we subtract 1 over 2 factorial x squared? Oh, whoa, look at that already. Okay, and then we're gonna add 1 over, what's 4 factorial the same as? Look at that. And then what about 6 factorial?
720.
Yeah, let's add another one. Plus 1 over 8 factorial. Oh. Is that 40,320? Oh no! So close. It's the exact same thing. Okay, help me out. We need y equals 1. Oh, okay, thank you. Ready? Whoa. And we can keep doing this, and it's just gonna get closer and closer and closer the further we go out. One more? Okay, I need 10 factorial.
3,628,800.
And the more terms we add, the further out it's going to approximate our curve. Okay. And eventually we'll talk about a radius of convergence. Oh, it's going to be so great, but we'll focus on polynomials right now. Okay, we are going to write a Taylor polynomial for y equals sine of x at x equals pi over 4. This will be the last one. This one's going to be nice too, right? So our function is sine of x. And when we plug in pi over 4, we get radical 2 over 2. Our first derivative is cosine of x. Also radical 2 over 2. This assignment is going to feel more tedious than it is difficult because we just got to keep trucking along with these derivatives and evaluating the derivatives the number of times it specifies. Okay, so I sort of made these open-ended, but we're going to talk here in a moment about vocabulary. It will always tell you what degree of polynomial they want you to go to. Okay. Always does. Do you see a pattern? Oh, these cyclical derivatives. we're gonna have like just this pattern, right? Positive, positive, negative, negative, positive, positive, negative, negative. Okay, so what's gonna happen is when we find our polynomial, we are going to take f of pi over 4. And we're going to add the first derivative over 1 times x minus a to the first. Remember, we're centered at x equals pi over 4. We're not centered at 0 anymore. Okay. Then we'll add the second derivative over 2 factorial times x minus a to the second. Should have written smaller. Then we'll add our third derivative over 3 factorial times x minus a to the third, etc., for as long as we need to. Now, I don't mind you leaving it like this. Some of you may prefer not having a fraction in a fraction. And so writing this might feel better for you. Combining those denominators together. Okay, and we could go on, but right now I think we get the point. Okay. Now, since this is centered at pi over 4, if we were to go into Desmos and do that grafting, we're going to be looking at pi over 4 and it's going to approximate it better. Okay, so we give it a whirl. Okay, so we have y equals radical 2 over 2. Okay, so here is pi over 4 right at that first intersection. Okay, and then we're going to add, it's going to be a pain. Then x minus pi over 4. Okay, notice how we get a little closer. And then we're going to subtract radical 2 over 2 times 3 factorial. Nope. That needs to be a 2 right there, right? You're helping me. Okay. And we're going to raise it to the second. Okay, so notice how at pi over 4 is where we're getting closer and closer to the curve. Okay, eventually we're going to fit closer to that red part over here on both sides of that curve. Okay, now let's talk about some terminology before I send you home for the weekend. Okay, the order refers to the number of derivatives required to write your polynomial. The degree refers to the highest power, and terms refer to the expression separated by addition and subtraction. So sometimes I'll say find the first 5 non-zero terms, which is not going to be a 5th degree. Okay. Order, degree, terms. We need to understand the difference between all of those and how it affects the question that I'm asking you. Second example, if I ask for the first 5 non-zero terms, that would be a polynomial of 8th degree, of 8th order.
exact 4 terms, would it be?
So I'm usually gonna say non-zero terms, so then it would, then the zeros. Okay, so you have a homework assignment. It's really not gonna take a lot of brain power because you're taking derivative, plug-in value, derivative, plug-in value, derivative, plug-in value, make a polynomial. Okay, so it's actually fairly light compared to the brain power that we've had to use for converging and diverging series tests, right? But go ahead, do your homework over the weekend, and then on Monday, we're gonna talk about the error in using the polynomials to approximate a value.